This presentation is going to give a brief introduction to prestressed concrete design and a brief overview of the history of prestressed concrete design. By the end of this presentation, you should be able to explain what prestressed concrete is and why we prestress concrete, describe the difference between prestressed and non-prestressed concrete beam behavior, identify the main limitation to early prestressed concrete, and explain what changed to make prestressed concrete feasible, describe the construction procedure for and differentiate between the behavior of pre-tensioned and post-tension concrete beams, and explain why the capacity of prestressed and non-prestressed members is approximately the same. Prestressed concrete is a type of reinforced concrete in which the steel reinforcement has been tensioned against the concrete. Tensioning operation results in a self-equilibrating system of internal forces. So essentially, when you tension the pre-stressing strands, the stresses in those strands is resisted by the concrete. So tensioning the strand puts the concrete in compression. Doing this creates a strain differential between the concrete and the reinforcement. So the main difference between conventional reinforced concrete and prestressed concrete is this strain differential between the strain in the pre-stressing steel and the strain in the concrete. We pre-stress our concrete members primarily because concrete's weak in tension. So in traditional reinforced concrete members, we provide steel where we have tensile stresses developing. In regular reinforced concrete, after cracking occurs, there's a considerable loss in stiffness in the member. So by pre-compressing our concrete, we can delay when that cracking occurs. So pre-compression substantially increases the external load required to crack the concrete, and this results in a stronger, tougher, and stiffer beam. So you can see two drawings here, one of a non-prestressed and a prestressed beam. In the non-prestressed beam, before we have loading, you can see there's zero deflection, and there's, if you don't include self-weight, there isn't any compression or tension in the beam. When you add self-weight, you get some tension in the bottom, compression in the top, and when you add your service load, you can sometimes get flexural cracking that develops if your service load's higher than your cracking load. In prestressed beams, before you have loading, you have an initial upward deflection called camber, and before you have loading, you have compression in the bottom of the beam and tension in the top of the beam, even with self-weight included. Then when you add service loads, you can get either have still some upward deflection or slight downward deflection. But essentially you can design your beam to remain uncracked under service load. We don't necessarily provide pre-stress reinforcement to increase the strength of our members. The main reason that we provide pre-stressing and why we pre-stress our concrete beams is to increase our serviceability and stiffness in these members. So in a pre-stressed beam, when we're at our service load, we remain uncracked and we're limiting our deflections. In a non-pre-stressed beam at service load, we can often have flexural cracking in the beam. One of the early limitations of prestressed concrete was the availability of high-strength steel. For conventional strength steel with a yield strength of around 60 KSI, nearly all the pre-stressing is lost because of what are called pre-stress losses. So if you pre-tensioned the reinforcement to about 40 KSI, so about 2/3 of the yield stress, after you take into account creep and shrinkage, about 30 KSI of that 40 KSI would be lost because of the creep and shrinkage. So essentially all the work that you put in to pre-stress that reinforcement would be lost after creep and shrinkage happened. So pre-stressing really wasn't possible or practical before the creation of high-strength steel. Eugene Fresnel is often considered the father of prestressed concrete. He was a French engineer who built a number of elegant concrete arch bridges that were post-tensioned. The idea of pre-stressing actually came to him during a series of lectures by Charles Rabbitt. And Charles Rabbitt may have built the first pre-stressed concrete member, which was a 23-foot concrete cantilever in 1904. But Fresnel really made pre-stressed concrete more popular. So some of his initial recommendations were to use metals with very high elastic limits, so higher strength steel, submit them to very strong initial tensions. So this would overcome the loss in pre-stressing caused by creep and shrinkage, and also to use stiff concrete. Using stiffer concrete decreases the amount of creep and shrinkage that occur, which would decrease some of these elastic or these pre-stress losses that happen. You can see here to the right two of the bridges that Fresnel designed using post-tensioned concrete. Gustave Magnum was really the person who brought pre-stressed concrete to the English-speaking world. So Magnum was a Belgian professor who spent the period in World War II really exploring Fresnel's ideas, and he also carried out some research on pre-stressed concrete. Magnum was a very capable communicator in English and was a good teacher as well. So his goal in teaching was to really simplify complex problems. So he really made pre-stressed concrete accessible to all engineers. Magnum brought pre-stressed concrete to the US by helping to design the Walnut Lane Bridge in Philadelphia, which was the first pre-stressed concrete bridge built in the US. Fresnel and Magnum both worked primarily with post-tension concrete, where the concrete's cast first and then allowed to harden, and then strands are tensioned afterward, where the tension between the strand and the concrete occurs at an end anchorage block. So Heuer, a German engineer, was the first to use pre-tensioned concrete, where strands are tensioned before the concrete's placed and no anchorage devices are used. And one of the first things that he constructed using pre-tensioned concrete was these thin flat slabs, which were pre-tensioned with very small diameter wire between two buttresses at the ends, as shown here. So only a small diameter wire could be used to ensure adequate bond between the wire and the concrete. So because there was no end anchorage to transfer the stress from the anchorage device to the concrete, the transfer had to occur between the wire and the concrete itself. And this is when Heuer discovered what has now become known as Heuer's effect. So essentially when you tension a wire, the diameter of that wire will decrease related to the Poisson's ratio. And you're tensioning the wire before the concrete's cast. So after you tension the wire and cast the concrete around, when you release the strand wants to return to its original diameter, and the surrounding concrete resists that strand from returning to its original diameter. So this creates a good bond between the strand and the concrete, and it really helps develop these smooth strands in shorter distances than would be required if there was no tension in the wire. So pre-tension concrete really wasn't widely used until the invention of 7-wire strands, where you take 7 of these strands and put them together, or 7 of these wires and put them together to form one strand. Another innovator in pre-stressed concrete was Ulrich Finster. So Finster was a German engineer who developed the double cantilever idea for pre-stressing or for pre-stress construction. So this construction is still used today, and it was one of the ideas that really allowed pre-stressed concrete to compete in these in the bridge arena. So for longer span bridges. So here's an example of a bridge that he constructed over the Rhine River in Germany in 1962. So as mentioned, there are two main types of pre-stressing. There's post-tensioning, where the strands are tensioned after the concrete is cast and allowed to harden, and then pre-tensioning, where the strands are stressed before the concrete's placed, and then the concrete's placed, and then the strands are allowed to harden, and then the strands cut, transferring the stress from the strands or from the bed into the beam. The typical procedure for post-tensioning is shown on this slide. First, a member is cast with a duct inside or with a strand that has some kind of sheathing or wrap on it to cause no bond between the concrete and the strand. After the concrete's allowed to harden to a certain strength, the strands are then tensioned with an anchorage device on one side of the member and an anchorage and a jack on the other side of the member. So you can see the stresses are transferred from the strand to the concrete through these anchorage devices initially. After the strands are tensioned to their desired stress, and another anchorage device is placed on the other side of the member. And this locks in the strain differential between the concrete and the strand itself. After this, there's some free space typically between or within the duct, and that free space is then filled with either cementitious grout or some type of wax or grease. So as mentioned, when you're done tensioning the strands in a post-tension structure, you still have some space within the duct that's free. And that space needs to be filled with either wax or grease or cementitious grout. The type of material that you use to fill this space will affect the behavior of the structure. So if you use a material like wax or grease that doesn't bond with the strand in the duct, you'll get what's called unbonded behavior. In an unbonded post-tension structure, as you apply a load, the stress in the pre-stressing strand is going to evenly distribute throughout the strand length, because the only point of transfer of stress between the strand and the concrete is at the ends of the beam, at the anchorage devices. So you'll have an average stress along the length caused by loads, and then also you're going to get one or two larger cracks. So when you have a crack open up or two cracks open up, these cracks will grow, and you won't have distributed cracks along the length of the structure. In a bonded system where you're using cementitious grout, you still initially have some anchorage devices at the end to transfer the stress from the strand to the beam. But after you grout the tendon, then there's also a bond present between the grout and the strand itself. So when you apply additional loads in a bonded system, you're going to get a stress in the strand that changes over the length. So similar to a pre-stress system, which we'll look at later. So essentially, in a bonded system, when you apply a load, you'll get, and you apply a load past the cracking point, you're going to get distributed cracking along the length. So this is just some differences in behavior between bonded and unbonded systems. The typical pre-tensioning process is shown on this slide. The first step in the pretensioning process is to tension the strands in a pre-stressing bed. So this bed includes some end blocks that can hold the force placed on them by the pre-stressing strand, or it has some steel forms that are called self-stressing that can handle the force from the pre-stressing strands. So, when you put the stress in the strands using a jack here at the end and an anchor on this side, that stress in the strand needs to be resisted by something. So it's either resisted by the end block or by a self-stressing strand. So after the strand is tensioned, the concrete can then be placed. So here we don't have any duct because the concrete needs to bond with the strand. So stresses are transferred from the strand to the concrete through bond between the two. So here the concrete's placed, it's allowed to harden, and then after that the strands are cut, which transfers the stress from the bed to the beam. And at this point, the concrete is in compression, and the stresses are being transferred from the strand to the concrete through the bond between the two. So there's no end anchorage device, and through Hoyer's effect, which we discussed a few slides earlier. The pretensioning process can be expensive because of the cost of the bed, the cost of the end blocks, and the cost of formwork, which is typically steel. So in pretensioning, repetition can reduce costs. So this has led to many standardized sections. So there are standardized sections dependent on application and also dependent on region. So for bridge applications, many of the standardized sections are dependent on the state. So shown here is a Florida I-beam section with a 45-inch depth. So this is an FIB 45, common in Florida for bridge construction. Other states have their own standardized sections, and they're used within their states and built by precasters typically within the state. For building construction, there are other types of members. So shown here is a double T section, common for pre-stressed concrete buildings. And also here's a hollow core, which is another common pre-stressed section for buildings. Two other sections that are kind of more national sections. Here's a box beam, an AASHTO type BI 36 box beam, which is a common section for short span bridges in many states. And then also an I-beam, which is a little less effective than the bulb T sections that are found in many states. With pretensioned construction, the speed of construction is essential. So these pretension members are cast at precast plants, and these precasters want to turn over their beds every day. So it's important that they can have a concrete that reaches high early strengths. So they typically use type 3 cement, which gives it a high early strength, and they typically will release or transfer the stress from the bed to the beam at about 18 hours. And this allows them to construct one set of beams in one set of formwork every day. So as a designer, we'll specify two different types, or two different concrete strengths. We'll specify a release strength, which is the concrete strength required before transfer can happen. So before they can cut the strands, a certain concrete strength needs to be reached. And then also there's an ultimate strength that we'll specify. And this is the strength that we need to prevent cracking under service loads and also provide sufficient strength for ultimate loads. As an introduction, we're going to go through some just basic design concepts that we'll cover later in the class. The first one is that we typically place our pre-stressing where tensile stresses develop. So here in a typical beam, We have tension developing in the bottom, so we need to resist that tension, and we put our pre-stressing in that location. One design principle that we'll look at later is an idea called the kern points. And essentially, if we place our pre-stressing within these two red lines or kern points, we can ensure that our beams will meet all of our stress checks. So we can ensure that our concrete doesn't have too much compression, and also our concrete remains uncracked. So again, these are a few things that we'll look at in later presentations. The next general concept we mentioned already, but tensioning of the pre-stress reinforcement is going to pre-compress the surrounding concrete, which will be able to give it the ability to resist higher loads prior to cracking. So here we have a pre-stressed beam on the left and a non-pre-stressed beam on the right, and we'll assume here that they have an equal AP FPS to AS FY. So they essentially have an equal tension force from the steel and pre-stressing components. So here with the pre-stressed beam, you have an initial deflection under no load, and this is called camber. The non-pre-stressed beam, you have no load, no deflection under no load because it's not pre-stressed. So as you load, they'll have a similar stiffness as long as the cross-section's similar up until the point when cracking occurs. So cracking in the non-pre-stressed beam is going to happen at a lower force than the pre-stressed beam. After cracking, the two beams will have a similar ultimate capacity. Pre-stressing will not greatly impact the ultimate strength generally. So if you have an equal tension force provided by your pre-stressing and your non-pre-stressed steel, we can remember from our equation for moment, it's dependent on the tension and the lever arm between the tension and compression forces for singly reinforced members. So you can see if you have an equal tension component from your non-pre-stressed and pre-stressed steel, then you'll have an equal moment, just analyzing the capacity using a rectangular stress block approach. So again, generally, pre-stressing is not going to greatly impact the ultimate strength. We mainly use it for serviceability to prevent cracking and to limit our deflections. Prestressed concrete can be used in all different types of applications. So about 50% of all of our bridges are constructed with prestressed concrete. Many, maybe most parking garages are constructed with prestressed concrete. Many office buildings are constructed with prestressed concrete, and other structures can be constructed with prestressed concrete. So water towers, nuclear containment structures, storage tanks, other towers and offshore structures can all be precast. And you can see here that precast concretes can also have some nice architectural features. So it's also used for cladding elements. So shown here is the Lake Erie College of Osteopathic Medicine building in Bradenton, Florida. And this was a structure that was constructed by Core Slab. So as I said, many parking structures, maybe most parking structures are constructed using precast concrete. So shown here are 6 different examples of precast, pre-stressed parking structures that were all constructed by Core Slab in Miami. So you can see that these structures they're all unique and you can get some nice architectural finishes on all of them. Another benefit of pre-stressed concrete and precast concrete construction is the dramatic increase in the speed of construction compared to cast-in-place construction. So here is, as an example, is the Burdines parking structure constructed by Core Slab. So you can see that the precast erection from the beginning to the end took 11 weeks. So here's February 24th, and 11 weeks later, the structure was open for business. So this is a dramatic improvement over the speed of construction for typical cast-in-place structures. Shown here are some references for further study on the history of prestressed concrete.